What we're looking at here is torque in a motor. Again, this is really review of year 12 stuff, but I think it's worth doing. I found with electricity you've got to go through it a lot of times before it becomes sort of natural. So this is my version of a coil in a magnetic field. The field's going from north to south, so the field lines across there, I won't put them in. I suppose I could put them in, but what I want to work out here is the torque. So right hand rule for everything, north to south, that way. Now with a motor you've got to have a current direction, so we'll put our current direction that way. Goes up that side, comes down that side, so that would be the plus, that would be the minus. And so we go right hand rule, north to south, current direction that way. So we know we've got a force down on that side, and if you have a look, you'll see that the force goes the other way on that side. So that's our force. So that's in the horizontal direction between the field. Now when you look at this, when you get up to the vertical position, what would the torque be? Let's actually work through the torque in this position, then we'll talk about that. So a little bit off with that. So what is the force? We've already done, we've gone from the Lorentz force law in another video, you can look at it, and we've come up with the fact that F equals BIL. That came directly from the Lorentz force law, this being L the length of one side. So we know the force on that side is F equals B, the field across here, I, the current we've got flowing in there, and L the length. So that's our F equals BIL. Now we know that torque equals force times the distance. What distance are we talking about? In this case, that force is down. We need to give that distance across here a measurement. We'll call it R. So we can say the force, and there's two of them, so we'll call, or the torque, we can say is equal to 2V I L, which is the force, times R, right? BIL is the force, that's the distance from the torque equation, and there's two of them because there's two sides. So if we actually have a look at that, we can actually say, well, 2 times the length times the radius, right? Length times 2 radii is area. So we can actually just call that B A I. So we can say the torque equals bi. Sounds like a Chinese word, doesn't it? And it is a Chinese word, but not today. So if we've got more than one loop, we can put an N on there. We call N, number of loops. So torque equals BANI, but I don't like BANI. I'll call it torque equals BANI. Now we can get back to that issue I was just talking about, which is what is the torque going to be when it's in the vertical position. So if we have a look in the vertical position, we've got our loop coming in, going vertical if you like. The problem is, at this point, if we do our right hand rule, it's not a problem, but if we do our right hand rule, and we've still got the current going this way, I know it looks a bit crap, but you get the idea, don't you? The magnetic field goes down that way. Magnetic field, right, we get current going that way, we're going to get a force this way, down. And if we do this one, down at the bottom here, north to south, alright, and current coming back that way, force is up. So you'll find that in the vertical position, the forces cancel, and so we don't get a torque. This one here, look at that one, north to south, down, it comes in. So again, no torque in the vertical position. And we work that out formula.